Okay, team, we're gonna get started with class here. Nice to see everybody. Welcome back to your penultimate lecture of this course. I was looking at our course schedule, and something confusing to me is that we've been consistently behind one lecture relative to what I wanted, but then I looked and today we're somehow caught up, and I actually couldn't figure out why. So that's cool, and later I'm going to figure out which lecture we accidentally skipped. But that's all right. So as a bit of review here, actually before we do that, of course, some reminders. Let's see, your final exam is next week? Next Thursday, 9 a.m. Is it this room? The room number was not my office, so I didn't recognize it. Okay, thanks, Leticia. Yeah, so this room, 9 a.m. next Thursday. Be there. Essentially, a bunch of you guys emailed me for alternative dates throughout the semester for your final, and then you all canceled it. So apparently we don't need an alternative final exam date. There's basically 2 people in this class that are away at SIGGRAPH Asia, and they'll have a 24-hour window in which to take the final exam, but they know who they are and what the procedure is. And the rest of you have got to be here, or you're not going to be happy with your grade in this course. Any questions, comments, concerns? Yes? We do have lecture on Wednesday. It is the penultimate lecture today. Second to last. Useless SAT word of the day here. Yeah. Are there other questions? Cool. And your TAs will schedule a practice session or whatever, a recitation exam review thing sometime between now and next Thursday, apparently. But beyond that, you're all done with your homework, which explains why there's fewer people here than usual, which is baffling to me because your homework is kind of not well aligned to the lectures anyway, but whatever. So basically, you've only got one more responsibility for this course. You're almost done. No big deal. I posted the previous final exam for the course on Piazza, Learning Modules, Canvas. So if you want, and I strongly suggest that you want to try a practice exam, there is one there. Might I also suggest retaking the current midterm and doing the practice midterm from last year. You've got a lot of practice materials out there. And again, you can do them more than once. My guess is that it won't be perfect each time. And if it is, then you'll be all set for the final, because we basically just have the same pool of questions. Hopefully you're starting to recognize some patterns. Cool. So the final topic of this course is all about integration of ordinary differential equations. And the basic idea here is that you have some unknown function of time. We're going to notate it as y of t in this course. And usually we're given some relationship between y and its derivatives, and your job is to integrate it forward in time, namely to predict the configurations of y moving forward. I think the most famous ODE out there in the known universe is f equals ma. Of course, when we say that, what we really mean is that f, the forces in your system, really only depend on positions and velocity, right? And m is a constant. It's just mass, at least in ODE world. And so essentially f equals ma is just a formula for acceleration in terms of forces, where forces are written in terms of the lower order derivatives of your function. So really Newton's law was just an ordinary differential equation. It's just at the time he wrote it down, ODE wasn't really a thing, so he had to use a bunch of words. If you read these old 18th century math textbooks, they're kind of funny that way. But in any event, in our previous lecture, we talked about 2 different algorithms for solving ODE, which were forward and backward Euler. These are 2 of the most famous algorithms out there, and also very simple ones to derive and code and all that good stuff. By the way, if you pronounce it Euler, then you will fail your exam. And right, so forward and backward Euler basically make very simple approximation. They say the following: if I want to solve an ODE of the form y prime equals f of y, then essentially, what do I have to do? Well, I can discretize y prime as maybe yk plus 1 minus yk divided by h. Remember, this is just to kind of recall the notation we're using in this course. And remember, this is a first order approximation of the first derivative of y, where here we're thinking of yk as like equal to y at k times the time step, like that. And On the right hand, we have f of y, which might be f of yk. Notice in this case, we can just reshuffle the terms here and get an expression for yk plus 1 in terms of yk. So in other words, we can predict the future given the current state of our system, right? If I do that, this is the forward Euler discretization. And if instead of that, I put yk plus 1 here, so I have plus 1 minus yk over h f of y. Notice this is not a formula for predicting the future because there's two yk plus 1 there. It's like a system of equations. But if I can solve it, we showed we still get a first order approximation for yk plus 1. This is called backward Euler. Does anybody remember why we might prefer forward Euler over backward Euler or vice versa? These are good questions to ask on final exams, in addition to just being things you should know in life. Yes, Alice. Yeah, so there's sort of a trade-off between stability and efficiency, right? So in particular, notice that forward Euler is relatively efficient, meaning that like it's just a formula to evaluate. But what we showed is that it has a radius of stability, meaning if h is too large, it can go out of control. Whereas backward Euler, you can have as large an h as you want, and at least we showed for the model equation, it never goes out of control. It always kind of converges in a nice fashion. On the other hand, this guy is less efficient to solve. In fact, we'll see that in a second. Even if we extend ever so slightly our model equation, so let's say that we do the model equation in multiple variables, so like y prime equals ay, where now y is a vector and a is a matrix, then I think a thing you guys could all work out pretty easily are these formulas for advancing y forward in time. Notice they're basically, I see your hand, they're basically the same as our one-dimensional formula. Hopefully we all agree with that. And notice that the forward Euler formula is matrix multiplication. The backward Euler formula, even for our model equation, is like a linear system of equations. And we know, if there's one thing we know in this course, it's that that second one is more expensive. Yeah? All right, Jonah. Yes? No, actually, this is correct. So what we've done here, in fact, we'll derive it really quick, is the following. So our model equation in this case is just the thing on the top of the slide. So we have yk plus 1 minus yk over h is equal to, in this case, a yk plus 1, right? That's, hopefully we agree, it's backward Euler. So all we've done for this formula here, this is implicit. You're absolutely right. There's two yk plus 1s. But notice we can rearrange this expression. So if I multiply both sides by h, then what am I going to get? Let me see. So I'll get yk plus 1 minus h a yk plus 1 is equal to yk, like that. And this is I minus h a yk plus 1. So this is a linear system to solve. Yeah, great question. Incidentally, if you do one step of Newton's method for the kind of generic nonlinear version of this integrator, you'll get exactly this system. Yeah, good question. Any others? Yes?
Yep, yk equals I minus ha yk plus 1. But then there for backward Euler, you have yk plus 1.
Yes, because I multiplied both sides by the inverse of the matrix. Absolutely, yes. You guys are trying to catch me. Uh-oh, on. What if it's ranked efficient? That's a good question. Let's see if we can come up with an example of such a thing. I believe this corresponds. Right, so let's see. That's a good question. I don't have a good answer for you immediately. My guess is it means that you have no business solving the ODE to begin with, but rather than thinking on my feet, I'm going to defer that and we'll think about it at the end of class. It's a totally reasonable question. Yeah. This can, I think, is more common to happen when it's not just a linear system of ODE, in which case, I don't know. Yeah, so I suppose, like, yeah, if I took h to be 1 and a to be the identity, that's a perfectly well-defined. Okay. Yeah. Now I understand. Okay, so here's a good example. Right. So the question is like, what happens if this matrix inverse doesn't exist? This is actually a case where you shouldn't have been solving this ODE to begin with. So remember in our previous lecture, we talked about stability of the differential equation itself. So think about what has to happen. So suppose that this thing is not invertible. So for example, if I took A to be identity and H to be 1, but in that case, you're solving y prime equals y, which blows up in time, which means that like, sure, yeah, this is an invertible, but also like your ODE is blowing up anyway. So what's division by 0? So I think typically when we talk about these things, we restrict ourselves to ODE that have solutions and don't blow up your error over time. Good question. Sorry. Okay, here's the thing. So these are two ODE solvers of many, and I think in general, unfortunately for us, this is one of these areas of math that doesn't have just like some magic theorem that just tells you exactly which integrator to use. And that's why, like if you go into mechanical engineering or a lot of other departments here, you'll see there's entire courses on choosing ODE integrators for different problems. This is like a whole art as much as it is science. And in general, what you'll see is that there's some trade-off between a bunch of different aspects. So in particular, there's accuracy and efficiency and stability. Stability. So for example, when we compare forward and Euler and backward Euler, we saw that one was more efficient and one was more stable. And they're actually both equally accurate, at least for small h. Does that sound familiar? And so these are the kinds of trade-offs. And unfortunately for us, there's like this giant Pareto frontier of different ODE integrators that kind of have different trade-offs between these considerations and often other ones, which unfortunately leads numerical differential equations to be this kind of crazy area of applied math where like there's so much room to propose new integrators for different problems. People do it every year. And like it's kind of interesting that way. Like there's not just one formula for choosing a standard thing. I mean, even if you like download a bunch of standard software that solves these things behind the scenes, like ANSYS, you'll find that there's like a bunch of buttons behind the scenes for just choosing different integrators and seeing what happens. And by the way, I should note that these are the three, this is like the, Math 101 version of this story. There's, of course, a long list of other considerations you might add to this for ODE integrators. So, for example, maybe you want whatever linear system you have to solve to be sparse or structured or positive definite in your integrator, or a very typical one. Notice that when we talked about accuracy, like a forward and backward Euler, and we'll see a few more momentarily, we talked about it in terms of Taylor series, right? Like small h. And that for a lot of applications, that's not actually what matters. So for example, if I'm playing a video game, then maybe I actually don't really care about the accuracy of my physics, but I really don't want it to blow up over time. Like these kinds of things, which can happen if, like, for example, forward Euler is first order accurate, but one thing that you can convince yourself is that, like, for typical physics systems, if you do forward Euler integration for any h, you will add energy to the system in every step. So if you play your video game long enough using forward Euler, eventually like everything will just be literally exploding, and that's not so great. So there's entire other classes of integrators out there whose whole job in life is, for example, to preserve energy or momentum over time. And that would be kind of like stability and accuracy, not in a small time regime, which is what we've talked about so far, but amortized over a long period. So for example, on your homework, you didn't know it, but you actually derived such an integrator. If you recall, you proved that a particular thing, I think it was symplectic Euler, has this property that it preserves the energy of your little pendulum flipping back and forth. Which if you think about it, what that means is that you can't have a case where like the kinetic energy of this thing just blows up and goes off to infinity, or where this thing just settles in its rest position, right? It just happily swings back and forth forever, which is not going to be the case if you apply these two integrators here. Does that make sense? So this is all just to tell you, unfortunately for us, we only have 2 lectures left in this course. But you can do an entire semester worth of these things. I have a book on my shelf that I absolutely love. It's called Geometric Numerical Integration. It's like this big. And it's just like this whole dictionary of different numerical integrators you can choose for different problems. So much fun. Okay, but let's talk about just a few other ones. So far, we've talked about this trade-off between accuracy, efficiency, and stability. But all of our things have been first order accurate. A reasonable question might be, can we cook up a higher order accuracy time integrator that kind of looks like forward and backward Euler? And of course, my answer is yes, or else we wouldn't be doing it. Now, so far, our arguments have basically just been Taylor series arguments. And so like, notice that the accuracy of forward and backward Euler basically just came from our lecture on divided differences for derivatives, right? It's just a byproduct of those formulas. And so how did we get higher order accuracy for derivatives? Do you guys remember? Oh, wait. Stack two of them together. I'm not entirely sure what that means. But to give you a bit of a reminder, if I have a function of time and I want to evaluate the derivative, so far our derivative has been like evaluate the derivative here by subtracting these two values and dividing by h. That gave us a first order accurate formula. You're whispering the answer to me and I appreciate it, but a little more. What was that? More points. In fact, we can, even with 2 points, if we just think of our derivative as being evaluated at the center point of an interval, then remember we can get a higher order accuracy formula, right? This was the difference between center differences and forward and backward differences for derivatives. So let's write out that formula since apparently we were all asleep. Right, so what can we notice? We notice that yk plus 1 minus yk divided by h, well, if we think about it, this is equal to f of yk plus 1/2 plus order h squared, right? Really, the order h squared, we're used to being on the left-hand side of this expression, right? Which is just to say this, remember, is y prime at k plus 1/2, right? And this plus this is also y prime at k plus 1/2. That was the expression that we had for center differences. Does it sound familiar? Because you guys are awfully quiet this morning. You're kind of scaring me. Okay, cool. So if we rearrange these expression, our center difference formula says that yk plus 1 is equal to yk plus h f of yk plus 1/2, like that. And now we've multiplied both sides by h, so we get an order h cubed, like that. Now, that's great, but our goal in ODE is to predict the future, and now we have two futures. There's yk and there's yk plus 1/2, or yk plus 1 on the left-hand side, yk plus 1/2 here. So this doesn't really give us a way to predict yk plus 1 in terms of stuff we already know, right? There's something we don't know here, and moreover, it's a different thing than the other thing we don't know there. So this is kind of underdetermined. Does that make sense? So here's what we can do. We're going to synthesize all of the things that apparently we forgot from our last couple lectures here. And that is, we're going to see if we can replace this value with something else. Yeah? And in particular, from our trapezoidal integrator, we have another expression here. I'm going to write it down first, and then we'll kind of bond with it a little. Let's say that I want to evaluate f at yk plus 1/2. Well, we can write that as f at yk plus 1 plus f of yk divided by 2 plus, it turns out, order h squared. So this came from a symmetry argument that we had. So if you go back to our derivation of the trapezoidal integrator, you might remember what we did is we took a Taylor series for functions kind of about the center point. And that we showed this like kind of nice property that like when you average things on both sides, the linear term cancels. And so what you're left with is something quadratic. And so thanks to this expression, we can substitute that into our expression for yk plus 1. And now we're going to get yk plus 1/2 f yk plus 1 plus f yk plus order h cubed. Cool. By the way, these are like the kinds of like reindeer games that we play when we're deriving numerical integrators. It's like there's a lot of things that are equal to each other up to big O of h or h squared or whatever. And like for every one of those that you substitute in, you get a different numerical integrator by just doing that. Yeah? Yes? Almost certainly. Am I missing an h? Yes. Thank you. Okay, so this integrator is called the trapezoidal time integrator. Notice that it has a yk plus 1 on two sides of the system. So this thing is itself an implicit integrator in time. But unlike our previous integrators, notice that the term that we're omitting looks like order h squared, which from our terminology in the previous lecture means that this is a second order accurate integrator. Remember, because we kind of have like a factor of 1 over h, which is the number of steps that's implicit here. Which gives us yet another way to integrate called the trapezoidal method, which is given here. Notice that this kind of looks like the average of a forward and backward Euler step. If we apply it to the model equation, we're not going to do that here because it's kind of boring. It looks very much like this proof on the board. Then what we get is this funky expression for yk plus 1 in terms of yk. And notice what it's doing. It's kind of like taking one step of forward Euler and then one step of backward Euler. Kind of cool that. Now, the trapezoidal method, in fact, so let's take this formula and make it specific to just a 1-by-1 problem. Then you get this expression here. One thing you can convince yourself is as long as a is negative, which remember corresponds to our stable case in the model equation, that this is unconditionally stable. The way that you argue that is remember that you look at this fraction and you just want to make sure that its absolute value is less than or equal to 1, which you can kind of get by eyeballing when a is negative. However, this thing has some funny drawbacks. So first of all, notice that this is an unconditionally stable second-order accurate time integrator. That feels pretty good, right? Because we had, so far, we had an unconditionally stable first-order accurate time integrator, which is backward Euler, right? So a reasonable question that you might ask is, like, is there ever a case when you should use backward Euler? Because somehow this feels like it's got all you could want and more, right? Like backward Euler was first order accurate. This thing is second order accurate. Both of them are implicit, so they're like roughly the same algorithmic efficiency. Does anybody have any ideas? Yeah.
Is it possibly going back to the argument that the trapezoidal thing is like 1 over 12 and the other one's 1 over 24? So while it's algorithmically the same, it's not actually as good.
That's a reasonable question. So Jonah points out that like the trapezoidal integrator we talked about as probably something you wouldn't use for like quadrature because midpoint integrator is actually more accurate. We actually don't have sort of a midpoint equivalent in numerical ODE, at least that we've introduced here. For second order ODE, there's a pretty reasonable one. So I'm not sure that intuition is exactly right, but you're absolutely right that there's some counterintuitive things that happen here. So here's the thing. Why do I like unconditional stability? Well, I like it because I can use really large h, right? And at least my thing doesn't blow up. Now, for large h, this thing doesn't blow up. It certainly goes to 0. But notice that that has nothing to do with the accuracy of this integrator. Our accuracy statements are all about small time steps. And in particular, can anybody make an interesting observation about this particular formula when h is really, really big? Remember that a is negative. Yeah. It oscillates. In particular, if a is negative, then the denominator here is positive, right? But if a is negative, notice what happens in the numerator. If h is large enough, then eventually the numerator becomes this very negative value. And so the trapezoidal time integrator has this really strange property that it's stable, but it's pretty useless for large time steps. In fact, it has some oscillatory behavior. So here's an example of what it looks like for the model equation. And you can see that indeed it zigzags its way into 0, but it does so in a way that I would argue is not very representative of an exponential curve. And so I think this is an interesting example of a time integrator that I think gets used for sort of mesoscale problems, where like an explicit integrator isn't going to work because for whatever reason there's a really tough time step restriction for like forward Euler. But you need your time step is still small enough that you can benefit from the second order accuracy. Right? So for example, in computer graphics, this thing isn't terribly common because in graphics we don't care about accuracy all that much, but we have short attention spans, we want to take big steps. And for really big steps here, the qualitative behavior of this integrator really isn't so good. Yeah?
So if h is very large, would you use backward Euler?
Probably, yeah. Or some other alternative to backward Euler we haven't covered yet. But that's right. For really large h, probably backward Euler. I mean, both of them are sort of equally crappy from a accuracy perspective once h gets big enough that the Taylor series is relevant. But at least this one doesn't give you an answer that like zigzags in some fashion that you wouldn't expect. And by the way, all of these things, the model equation is obviously a very simplistic perspective, But I think it really does illustrate the kind of qualitative things that happen at some scale in numerical ODE. So, for example, if you solve a certain cloth simulation problem with this, I think you'll typically see kind of a wiggly piece of cloth come out. Okay. So this is exemplary of a certain pattern we see in this discipline, which is that convergence as h goes to 0 is not the whole story, nor is stability, that there are these sort of medium scale considerations that we might consider kind of for fixed positive time steps. This is one simple example. If you go and take advanced courses on this topic and you talk about energy momentum conservation and so on, then you'll see that there's all kinds of really beautiful properties you can build into these integrators that are kind of interesting. Like, it's a lot of this area is kind of based on vibes, because at some point, like when h is large enough, you really don't expect to get a good solution to the original ODE, but you do still expect to kind of preserve some large-scale behavior of your ODE. And a lot of times there's a lot of a kind of a theoretical disconnect between what you can prove and what you can show. So for example, a lot of these integrators that preserve really nice structures are often used to take large time steps for physical experiments, and they are sort of borne out by practical experience that these things are good approximations, but actually proving it can be quite a challenge. Because at the end of the day, our main machinery for proving approximation quality is Taylor series. Okay. Now let's talk about 75,000 other classes of integrators. There's so many, I can do this for days. And they all have beautiful properties and they're all fun to derive because they're just like different little math tricks. So far, the math tricks that we've been applying are basically Taylor series math tricks. Here's a fun thing that we can do. We can actually take any of our quadrature rules from the previous lecture and turn them into a numerical ODE solver. And so I thought I would give you a flavor of how to derive that. And then we are going to quote probably the world's most common explicit time integrator, but we're not going to derive it because it's ugly and I hate it. So here's our story so far. Remember that we have, by the way, hopefully you remember from our previous lecture, we showed it's sort of sufficient to solve this first order ODE by a series of reductions so long as our functions are vector valued. We're going to return to this assumption in a minute. So if I integrate both sides of this expression, just dt, then what I'll get is, of course, yk plus 1 is equal to yk plus the integral from tk tk plus 1 f of y t dt. Yeah? So here's kind of a fun thing that we can do to derive time integration rules very efficiently, which is as follows. We can basically take any of our quadrature rules and put them here. And for each one of those, we get a new time integrator. Yeah? So for example, our trapezoidal integration formula actually already showed us that this is equal to h over 2 f of yk plus 1 plus f yk plus big O of h cubed, which in one line gives us the integrator proof that we wrote on the previous proid. You see that? Sneaky, huh? But it turns out that a whole series of integrators can be written this way. Basically, this is just a fundamental theorem of calculus, by the way. And so let's actually derive them. So here's a fun thing that we can do. Let's say that I wanted a Let's say that I wanted something with this property, but I also don't want it to be implicit, because implicit integration is expensive, right? And remember, the name of our game here is that like Taylor series are fine, and we can just stick them in all kinds of different places, and as long as we incur anything with order h cubed, we're good. So in some sense, what is the pesky term here? For our trapezoidal time integration, it's sort of this guy right here, right? That's what's creating our implicit systems. This is this f term. Yeah? Now here's an entirely new strategy of integrators. These are called RK integrators. You've probably heard of them before. They show up in video games a lot. And these integrators do the following. You start with a quadrature rule like this guy. Now, you have a bunch of terms that are going to make your integrator implicit, which is fine. Like, there are plenty of integrators that are implicit. But here's a different thing that I can do. I can actually take, I make one additional observation, which is really, really sneaky. Notice that this term is scaled by h. Think about that for a second. I can make a bad approximation of this f term, and it gets scaled by a small number, so its badness kind of shrinks as a function of h a little bit more aggressively than stuff on the outside. That makes sense? So for example, if I made an order h approximation of f of yk plus 1 here, then I'd actually incur an order h squared term for my original integrator. Sneaky? So here's what we're going to do. We're going to apply the formulas that we've already written down recursively. In particular, notice that this is the same as yk plus h over 2. And here's like a really crazy idea. I'm going to have f of yk plus h f of yk plus order h squared, all inside of f, plus f of yk plus order h cubed. What did I do? I just took forward Euler integration and substituted it in for yk plus 1 inside of my evaluation of f. Do you agree that this is kosher so long as I leave this O here? Right, because these two things are just equal up to that O term. Now here's a really sneaky trick. Oh, this is so cool. So f for suitably differentiable problems also has a Taylor series, right? And what does my Taylor series look like? Well, if I take my Taylor series about this point, then if you think about it, it's equal to this guy plus some darn thing times order h squared, right? Basically, there's a linear term here, which is what's going to predict the difference between evaluating f here and evaluating f at the sum of these two things. But it's linear, so in particular, it just looks like h squared. So basically, if you think about it, this is a really simple argument to just pull that order h squared out of the f, like that. That order h squared gets scaled by the h on the outside. So really, it can be absorbed into the order h cubed here. And what you get is another time integrator. Ta-da! So what do we do in this particular formula? It feels like I did magic because I kind of did. So here's the way to think about this thing. Remember that, like, let's say that we're solving the model equations. So in principle, we want some nice decaying exponential like that, right? Our forward Euler formula is going to just like make some prediction like this, right? Now backward Euler integration, what does it kind of want to do? It wants to like evaluate f somewhere along the curve that I have to find at some point in the future, right? So what is this integrator doing? It is predicting the future of the system, evaluating the value of f, and then just kind of pulling it back to original point. This is a whole series of schemes that kind of go back and forth. They're like trying to predict a value at time equals 1. So they like do some bad integration forward. They predict that value. They integrate it backward. They predict again. And you can kind of go back and forth. In fact, one thing you can convince yourself is this is kind of like one iteration of Newton's method applied to the backward Euler system. And this particular integrator is an example of a much larger class. So this gives us a particular integrator called Hoynes' method, where essentially what we do is every time we have some implicit term, we use a lower order integrator to predict the input to that implicit term. And we just make sure that it is paired with an order h on the outside so that it preserves the accuracy of the whole thing. Does that make sense? Now to be absolutely clear, this is not the same as trapezoid method. In fact, trapezoidal method is unconditionally stable. This thing has a stability radius, so you have to be a little bit careful using it in practice. We're not going to derive it because it's just an ugly formula. But the stability condition, if you're curious, looks kind of like the stability of the forward Euler method. In fact, it's exactly the same. So this is an example of a strategy that's used to derive a whole class of numerical integrators called RK integrators. I'm not going to attempt to pronounce these two people's names. Every year I intend to look them up, and then I don't. Where essentially what you do is the following. It's like always the same kind of systematic strategy. You apply some quadrature rule to approximate this integral. This thing is going to be written in terms of evaluations of f at different points in time. And then to get those evaluations of f at different points in time, you substitute in explicit integrators of the proper order, and you just make a Taylor series argument that says that's good enough for approximation quality. Yes? You have to be careful. So Euler integration is a first order accurate integrator, but this thing is second order accurate. Oh, that's a good question. Like, is that stability region somehow a mistake or like a happy coincidence? No, I think you're absolutely right. That like essentially for stability, what ends up happening is that like the stability is sort of limited by the stability of the one of the integrator pieces that are going into the formula. I don't know that offhand for all of them, but I think something like that is true. Yeah, it's a good question. But anyway, so this is a very systematic strategy for deriving a whole set of integrators. In fact, if you take a big class on this stuff, you'll derive this fun little like tabular way to derive RK integrators, which basically takes this proof and puts it in a table. I consider that to be a little bit useless because you can just Google it. But there's a whole series of these things where you take any of your favorite quadrature rules for that integrator there, and then plug in this little strategy here. And in particular, it is worth noting, and not deriving because it's ugly, it's a similar version of this proof here, one of the integrators which is particularly common in practice. I think this is the sort of default option in most ODE integration software, which is called RK4, which is fourth order accurate. And basically, it does exactly the same argument as what we wrote here, but rather than doing trapezoid rule for this integrator, we do Simpsons. Remember, that's the one with the parabola? If you go on Wikipedia page for the RK4 integrator, you'll see this really crazy illustration that I consider totally useless, but it's kind of fun that somebody tried to do this. Where like if you kind of stare at this integrator long enough, you can kind of see what it's doing. So here, notice K1 is like the slope at your initial point, right? So then what happens here, you kind of go half a time step with forward Euler, right? That's what this thing is. And then you evaluate the slope there. And that gives you the slope at the midpoint. Then this guy kind of does half a time step of some other integrator where you got the slope from half a time step of forward Euler. So anyway, Wikipedia manages to like draw all of these things on a time integral and show all the different interval and show all the different slopes. I never really bonded with that picture, but if you guys do, then power to you. Yes?
Can you please explain that formula in, like, with the diagram again?
Oh, sure. Yeah. So hopefully you see what's gone here is that essentially in Hoyne's method, I have this implicit, or sorry, in trapezoidal integrator rather, I have this implicit term here, which I don't really have access to. So what happens in these strategies is you extrapolate using a lower order integrator. Right? That's what's happening here. Now, the basic idea, notice that f of yk is kind of like a first order approximation of your unknown curve at time tk. And then in some sense, what happens in, for example, backward Euler is you're trying to kind of find the slope over here that matches the line through the point, right? Because it's evaluated at this other point in time. So the kind of intuition for why this accuracy is relatively small is that like you kind of wanted to evaluate the slope on your curve. You didn't really have that. You have this extrapolated guy from forward Euler, but it turns out these 2 points are close enough together for evaluating f. It's just a schematic. I wouldn't worry about it a whole lot.
The intuition for the formula is like, okay, like I don't know why k plus 1, so I'm going to do an approximation.
Right.
I think it might be based on my curve.
This is exactly right. It's like it almost feels circular, right? Like our whole point is to find yk plus 1. But the point is this particular incarnation of yk plus 1 is scaled by an h, so I can get away with a worse approximation of it. Yeah, great questions. Okay, so that's going to conclude our derivation of totally generic time integrators. Again, there's a million of them, and they all kind of live on this different frontier between stability and accuracy. I think a good just default is to use RK4 for like reasonably smooth ODE, and then work your way out into more complicated stuff from there. However, there are so many interesting advanced topics in here, and we're just going to touch the surface by mentioning 2 fun things that you can do in this domain. I'm going to try and do 2 complete things today and 1 more on Wednesday. This is an ambitious plan. I think we can do it. Okay, team. So the first one is going to continue on studying first order time integration. This is actually not a very well-known class of time integrators, but I wanted to give you guys a flavor of just like a very different strategy for time integration for these problems, and one that really challenges the assumptions that I think we've seen so far in our lecture today and last time. And that's as follows. Here's the thing about the model equation, right? So far we've used the model equation to evaluate stability of our ODE integrator. And the only reason that that's a useful thing to do is because our ODE integrators get the model equation wrong. Do you see that? Like, if they were perfect on the model equation, then it wouldn't really be a good way to understand stability because they're 100% stable on that thing, and then maybe there's just some other ODE where they blow up, right? And to make matters even a little murkier, we know the solution of the model equation, right? So in particular, even if A is a matrix, then we can write y of t equals e to the at times y0, where e to the at is kind of like take all the eigenvalues of A, exponentiate them, and then put them back. We mentioned this briefly earlier in this class. If that's uncomfortable for you, just think in one dimension, then like this is just e to the at for the scalar. It's perfectly fine here. I think there's this totally implicit assumption. When you see a typical lecture on numerical ODE, you happily use the model equation as a way to assess stability, accuracy, whatever. But we wrote down a solution for this thing. So it's kind of like, well, that's dumb. Like, why do we need, like, why are we assessing numerical integrators if we have a formula for this thing anyway? Somehow the real takeaway you should get is that our numerical integrators are all pretty bad. So here's a fun question you could ask. Can I cook up a numerical integrator that does perfectly on the model equation just to challenge our assumptions about stability and accuracy, right? Because then the notion of stability is not so great. So in particular, here's a class of differential equations that actually appears quite a bit in practice. This is pretty similar, for example, on your homework, you did that ISTA algorithm, which kind of said, like, what if I have an objective function where one term I know how to optimize, but the other one I don't? You could do a very similar thing for numerical differential equations. You could say, well, I know how to integrate e to the at. Like, that's not such a big deal. So what if I have an ODE of the following form? I have an ODE, which looks like y prime equals a times y plus g of y. And moreover, I think g is pretty small. This is actually very typical. I mean, like, this is kind of like saying I have a Taylor series for my right-hand side, and the first order term dominates. Now, if A, for example, is a matrix whose eigenvalues are on like some weird gigantic range, this could really be a problem for integration using the strategies we've talked about so far. So for example, if I have an oscillator, like just a spring going back and forth, then essentially the time step restriction that I'm going to have for my integrators typically is going to look kind of like the space between two oscillations of my spring, right? Because like if it's like wiggling back and forth, back and forth, back and forth, if you anticipate the future after like 1,000 wiggles, it's clearly not going to do very well with these integrators that are based on drawing straight lines, right? So one thing we could do is to try and bake in our solution like this and see what happens. Now, you guys have all taken an undergrad ODE class. You might remember there's actually a strategy in that course that also does a similar thing. You guys remember the name? This like comes from our long dictionary of like fun magic tricks that you learn in an undergrad class and then never think about again. Integrating factor. Yeah, I think that's one name for it. The one that I learned is something called variation of parameters. I always envision the 19th century mathematics as like you have like your court with your king and your whatever, and then the jester, and then there's like this court mathematician that like they know the trick for solving ODE of a certain form, so they can challenge other people's. By the way, apparently that literally is how the quadratic equation came about. Is you had your court mathematician and some guy figured out how to solve quadratic stuff, and that could blow all the other court mathematicians out of the water. Okay, so let's say that I want to solve an ODE of this form. One thing we can do is reshape it a little bit. So in particular, we have y prime minus ay equals g of y. Hopefully you all agree with me. And now we're going to do a really sneaky trick, which like I don't know who came up with this to begin with. Like these people are so smart, you know. Like this is neat. In particular, I'm going to multiply both sides by e to the minus at. So I have e to the minus at like that, y prime minus ay equals e to the minus at g of y. Cool? I can do that. I can do anything I want. Now, does anybody recognize the left-hand side of this expression? I certainly didn't when I wrote this down. Yeah. Wow. See, we got the sharp one this time. So if you think about it, this is d over dt of e to the minus at y of t. I think once you write it down, it's easy to verify in the forward direction here. So let's do the product rule. So notice if I differentiate, I get e to the minus at times y prime, right? That's the first term, plus y times the derivative of e to the minus at, which is just ae to the minus at. And so that's the second term here. Is that sneaky? I wouldn't have thought of this. So in particular, if we integrate both sides of this expression, what we're going to get is e to the minus a t y of t minus y of 0. Here I'm integrating from 0 to t. I've kind of overloaded t the tiniest bit. For that, I apologize. Notice that at t equals 0, the e to the minus at is just identity. What is that equal to? Well, it's equal to the integral from 0 to t of e to the minus a tau, maybe, just to disambiguate, g of y of tau d tau. Isn't that cool? I think this is such a cool formula. Like, I don't know who cooked this darn thing up. Okay, so what does this allow you to do? So let's reshuffle this expression ever so slightly. Yeah, I envision numerical ODE as being like the NeurIPS of the 19th century. You know, like you could cook up some boring idea by putting in a Taylor series and an exponent and make a new research paper. And that's like definitely what's happening here. So, okay, we have this expression. We're going to multiply both sides by e to the at. And what we get is y of t equals e to the at times y of 0 plus the integral from 0 to t of e to the minus. Now here's a kind of interesting thing. I multiply both sides by e to the at, and I can kind of combine that with this e to the minus a tau. So notice that I can write a t minus tau like that. G of y tau d tau. Cool? Now, here's a neat thing. Notice that as a happy byproduct, we actually proved the solution when g is equal to 0. So if g is equal to 0, notice that I just got that y of t is e to the at times y of 0, because this term just vanishes. But now I have this fun formula, and remember we already have a strategy using quadrature to derive new integrators for these ODE, where if I take these integrators, I can substitute in different approximations of this integral, and what I'm going to get are different numerical integrators in time. But these are fundamentally different from the ones we've derived so far, because now we have isolated out the effect of that linear term. Does that make sense? Now, this leads us to a whole class of numerical integrators called exponential integrators. Therefore, the class y prime equals ay g of y. So for example, the world's most uninteresting version of this says that this is roughly equal to, for example, like h times all of this stuff just evaluated at time 0, right? Like basically do forward Euler on this integral. And then what you get after some reshuffling is the expression on this slide. You can check the textbook for derivations, just arithmetic. But the reason that I mention these integrators is that they're totally wild and hard to think about in the framework that we've derived so far in this course, right? Because if I ask you for any exponential integrator, what is its stability? Your answer should be, well, it's unconditionally stable, right? Because if I put it in the model equation, that term is 0, so like who cares? I always get e to the at. Now the reality is that that's not true. I mean, I'm using forward Euler, but I'm only using it on this g. So in fact, to really think about these objects theoretically and carefully, you actually need to define an entirely new notion of what it means for an integrator to be stable. So in any event, I'll let you guys think about that and philosophicate a little bit on the proper approach to these things. But I do think it's actually suggestive of a really interesting larger strategy here, which is to say a lot of physical systems are like very close to ones we know how to solve, right? Like most physical systems are basically springs plus like a few accoutrements attached to the side. So like at the very least, like if you know how to solve simulation with the spring exactly, maybe you should bake that into your numerical integrator and then just deal with the part of your problem that you actually don't know how to integrate. And that leads to this entirely new class of methods. However, those methods are really hard to analyze. Now, computationally, can you guys think of any drawbacks here? You have to do matrix exponential. So in fact, to do this, so for example, if A is a symmetric matrix, if you're lucky, then like a very simple way to do it might be to compute the entire spectrum of A and exponentiate all the eigenvalues and then put it all back together, which is a very numerically expensive procedure. In fact, there's a famous document in the world of numerical analysis. I think it's titled 19 Dubious Ways to Approximate Matrix Exponential. And the entire point of that thing is that a lot of these formulas are not so useful in dimension bigger than about 100 because just computing e to the at is itself a very, very expensive proposition. In fact, one of the standard ways to do it is to use one of these ODE integrators, which of course means that the accuracy of this formula then is hampered not by this beautiful relation, but rather by the fact that you computed your exponential poorly. Your TA Leticia suffered from this about 3 weeks ago. Did you have another question, or was that related? Yeah, it's a problem. There are all kinds of nice approximations of matrix exponential, for example, using polynomials and rational functions and so on. Each one of those can be understood as a time integrator for the model equation, in which case it's not so clear that you got all the nice properties you wanted. Yeah, really good question. But in low dimensions, like for example, you have a low dimensional, very oscillatory ODE, where matrix exponential is not such a difficult thing, then this is a reasonable class. Isn't that fun? This is like a really neat formula. Okay, so we have 30 minutes left, which is not enough time to derive the thing I wanted to derive, but we're going to try, and then I'm going to get frustrated when we're out of time. Okay? So here's the thing that we did in our previous lecture that I think we should think of as rather, sus? Which is as follows. We took a second order ODE, like f equals ma. And the very first thing we did is we got rid of it, right? We replaced f equals ma with a first order ODE. And if you think about it, the basic trick that we did was what's shown on the screen here. So for example, here, if I have basically an ODE of the form, y double prime is equal to f, let me make sure I align with the notation, t y prime. We showed that it always can be written as like using a bigger vector y, right? We have to expand the dimensionality as a first order problem. So what did that show? It showed that any first order integrator can be used to solve higher order ODE. It did not say that the best way to solve a higher order ODE was to do that reduction. That is a common point of confusion. And in fact, second order ODE are very common in everyday life because of Newton's laws. Before Newton, they were just solving first order ODE. It was much simpler. So in particular, it is worth considering whether we can come up with integrators for ODE, specifically, for example, for the second order case. By the way, the strategies we'll talk about go to higher order, but there's relatively few higher order ODE that people think about. Whether we can come up with things specifically for the system on the screen that do better than that generic case we've talked about so far. And let me give you an additional hint. Let's say that I write the system of ODE that we see on the screen here. So here v is velocity and a is acceleration. Hopefully we all got that. Here's a kind of interesting thing. At the end of the day, for most of my physical simulations, which of these three quantities do I actually care about? Mostly I just care about y. Right? I just care about the state of my physical system. In particular, if I have a bad approximation of v, that might be okay. Yeah? In other words, like, here's an interesting thing we can do if we leave our ODE in this form, is what if I use a first order integrator for v and a second order integrator for y, and I put them together in a really careful fashion? Maybe that's actually okay and can save me in efficiency. Now, to give you a little bit more of a hint here, here's a Taylor series for y about tk. Let's say that I put in, kind of similar to how we derived like Hoyne's method, notice, what if I put in a pretty bad approximation for y prime? Well, that approximation is scaled by h, right? So if I have a low order Taylor series for this guy, I actually kind of gain a little bit of accuracy by virtue of this scaling, which, and similarly here, in fact, now we got an h squared, I can have a really bad approximation of the acceleration. And like that's scaled by a small, small number, so maybe that's okay, right? So that's the kind of interesting logic that we're unable to use if we do that reduction to first order, but if we expose all these different pieces, maybe we can leverage that fact. Does that make sense? So we're going to talk about two integrators, one of which is actually a class of about 5 gajillion different integrators, and then the other is just one really common one for Newton's laws that are worth being aware of. If I were smart, I would have done them in reverse order, given my time limitation, but I only have notes on the complicated one. And these are both strategies that try to leverage this decomposition here to come up with a whole class of integrators that basically deal with y prime or y and v in separate spaces. Does that make sense? So in particular, the thing that we're going to talk about today, I hope, is a class of integrators called Newmark integrators. Oftentimes you encounter this in structural engineering software. It turns out that's a sort of common choice. Jonah's making a face at me, so I'm guessing he's seen like a button in a piece of software for dealing with these things. And Newmark integrator is an entire class of different integrators that are parameterized by different constants. And it's one of these things where you prove this giant, horrible, horrifying theorem, which we're going to do right now. Get excited. Which has all these different constants in it. And then what you can do is like read off different integrators by saying, oh, if gamma is 1/2 and beta is 2, then I get like midpoint. And if it's this and that, then I get this other thing. So it's like one of these useful ways to derive an entire class of things. Okay. Everybody put on your seatbelts and or check out and or open the course textbook and follow along, because there's going to be a lot of symbols that are about to happen. And I noticed there were a bunch of typos in the book this morning, so I'll see if we can fix them while we're at it. Okay. Everybody understand the high-level story here? Okay. That's really what matters. I'm saying this mostly because I know I'm going to get it wrong. Okay, so in particular, I'm going to start with a very deep fact, which is the following. Here, let's say that I want to predict v k plus 1, which remember is going to be v at time tk plus h. Well, this is equal to vk plus the integral from tk to tk plus 1 of a of t. I'm going to start with the hard stuff. Okay. So we already have this little fact. Here's a kind of interesting thing we could do is try to build this fact into figuring out an approximation of y at tk plus 1. But now we're going to need kind of more than one integral, it feels. In particular, here's the thing we can do. So let's say that we want y at time tk plus 1. We can apply the same formula, right? So in particular, we have that this is yk plus the integral from tk plus 1 of v of t dt. Hopefully I haven't made a mistake yet. Okay. Now I can do something very deep, which is follows. This integral is also equal to the integral of 1 times that quantity. Yeah. And notice that 1 is the derivative of t. Yeah. So does this allow us to do anything? Do you guys remember this trick? Yeah, exactly. This is integration by parts. In particular, here's the thing that I can do. Let me see. So what's the the AP calculus way to do this? You have like u and then dv. So like dv is going to be 1 dt. So then v is like t and u is v of t because I've chosen terrible notation. So then du is I guess v prime dt, right? But this is just like this useless little table that you do in like high school calculus over and over again. And so like the integral here is this guy, and you want like that guy, and there's like a diagonal, I don't know, whatever. So at the end of the day, we're going to get that this is yk plus, how does this work? You take the unintegrated quantities, so this is I guess t v of t, integrated, evaluated rather, at tk plus 1, right? So this means like evaluate this quantity. I'm sorry, I didn't write a clear t. Yes, of course it is. Hey, wait, what do you mean you can't read these scribbles? Minus the integral from tk plus 1 of t times v prime, but we know v prime is a. If you take my graduate course a year from now, you'll see that this is actually a life philosophy. Anytime you see an integral, the very first thing that you should do is see how you can wedge some version of integration by parts into this thing. just like a thing that everybody should do in life, anytime you see an integral. Yeah? By the way, I think if you read it backwards, this equation makes more sense. I think we're just not used to like an implicit 1 sitting there. The reason we're doing that is because we really wanted to engineer acceleration sitting into our formula. Cool? Okay, I'm going to erase this because I probably got it wrong. There we go. Neat. So, here's the thing that we can do. All right, so notice this is tk plus 1 vk plus 1 minus tk vk. Yeah. So if I expand that expression out, then I'm going to get the following. This is equal to yk plus, now we're going to do a sneaky thing, hvk plus tk plus 1 vk plus 1. If you're wondering, I went through like 6 different books that derive this integrator, and they all look equally ugly. Or they just don't do it. But we're all friends here, so we can do it. Okay. So what have we done here? This quantity is the same as tk plus 1 vk plus 1 minus tk vk, like that. And notice that tk plus 1 is tk plus h. Okay? So we've got tk plus 1, vk plus 1. So that's like this guy here, right? We have a minus tk vk, like that. And what we're going to do is say that that's the same as minus tk plus 1 vk plus h vk. Make sense? Everybody grok that for a second, because I know there's a lot of moving parts. Yes? Almost certainly. Am I missing? What? There's a yk. It's right there. No? I think we're good. Yeah, okay. So, everybody with me so far? We're going to continue to make this uglier, so get excited. Okay. So, why did I do all that work? Well, notice this is, of course, this quantity here is tk plus 1 times vk plus 1 minus vk. Yeah. Which conveniently for us, we have an expression for. Yeah? So what can we do? We can write this as follows. This is equal to yk plus h vk plus the integral, or sorry, plus tk plus 1 integral from tk to tk plus 1 of the acceleration of t dt minus this other integral. Like that. So all I did is notice that the difference in velocities is exactly the integral of acceleration. Whew. We basically only have 2 tricks. We just apply them like 1,000 times. Okay. And of course this thing, notice that these 2 integrals now are both integrals of a with just different factors. So we can combine them to write the most beautiful expression of all time, which is that this is yk plus hvk plus the integral from tk to tk plus 1 of tk plus 1 minus t a of t dt. All I did was combine these 2 integrals. This one's easy. Everybody with me so far? Notice that this is kind of like the second order analog of the expression we started for advancing v forward in time. Okay, so this turns out to be our sort of fundamental little formula for motivating these Newmark integrators. And now we have to make a horrifying Taylor series argument just to make our life a little worse. So let's see if we can do it. You might notice that I'm 1 out of 4 pages to go and have 10 minutes left in class, which is not good. Okay, so, but these are cool integrators, so I want to cover them. Okay. So I would be remiss in any lecture on numerical ODE not to have at least one Taylor series, so let's do that for now. So in particular, what we're going to do is take tau to be any constant between tk and tk plus 1. Okay? And this is going to be one of the many parameters in our numerical integrator. Now, here's a really weird thing we can do. We can write a Taylor series for tau, about tau, rather, and evaluate our system at time k and time k plus 1. Let's write down what that means. This means that ak is really equal to a of tau plus a prime of tau times tk minus tau plus big order, if you think about it, h squared, right? Because tau is somewhere in between those two time steps. And similarly, ak plus 1 is equal to a of tau plus a prime of tau tk plus 1 minus tau plus order h squared. Everybody agree with me? These are just Taylor series about tau evaluated at time tk and time tk plus 1. Go tau. So now, again, this just keeps getting worse. We're going to take this expression, and we're going to take a second constant, which is going to be gamma. And gamma can be any constant we want. Now, all of these different constants, like, it's perfectly fine in your mind to think of like gamma as like 7, like whatever. It's not going to matter. Basically, every gamma we're going to have is going to lead to a different numerical integrator. That's anytime you see these formulas where like it's a whole class of methods, this is what happens. So you just end up with horrifying expressions, whereas if you did any one case of this, it wouldn't be so bad. So if I take this first expression, but also this is the second to last lecture in a math class, so it should be ugly. We're going to scale it by 1 minus gamma, and the second one, scale it by gamma, and then we're going to add these two things together. And notice that there's an a of tau in both of them, so that's kind of nice. In particular, what I'm going to get is that a of tau is equal to, well, notice we have like a 1 minus gamma ak and a 1 minus gamma, or a gamma times ak plus 1, right? So we have 1 minus gamma ak plus gamma ak plus 1, like that, plus a prime of tau. And I'm going to skip a tiny step. Notice there's an a prime of tau in these two things. This tk minus tau is scaled by 1 minus gamma. This tk plus 1 minus tau is scaled by gamma. Then we add those two things together and simplify a bit. Then what you're going to end up with is tau minus h gamma minus tk, like that. Let's order h squared. So this just comes from multiply these two things together, and then remember that tk plus 1 is tk plus h. Cool? Now, why do we do that? I mean, essentially all I did is I kind of flipped our Taylor series backward. Like usually we think of Taylor series as like approximating a thing near tau. Here what we're doing is we kind of have the endpoints of an interval, and we're approximating the function at tau by kind of combining values at the endpoints. This is just like a different formula. Okay. So now, yes? These two guys? We are scaling this by 1 minus gamma and that by gamma. So there's no factor of 2 because these two things add up to 1. So you take this entire expression. Yeah. Okay. So, are you frustrated yet? Because we're about to do another ugly thing. Yes, quick. No, gamma can be anything, right? I mean, like nothing we've done so far. I think typically if gamma is crazy, you'll get a bad integrator, but that's a different matter. Yeah. Okay. So now, any idea what we're going to do next? I wouldn't if I were you. We can take this expression here and integrate it with respect to time. So in particular, what we're going to get, well, if I take the left-hand side and integrate it with respect to time, I'll get vk plus 1 minus vk is equal to the integral from tk to tk plus 1 of a of tau d tau, like that. That much is certainly true. And now, well, let's see here. So notice that these two terms actually have no tau dependence, right? So this particular term is pretty easy. So 1 minus gamma times hak plus gamma hak plus 1. Basically, I just took those two terms and scaled them by h. Okay. plus the integral from tk to tk plus 1 of a prime of tau, that was supposed to be a tau, that's tau minus h gamma minus tk d tau, like that. So basically I just integrated this expression here. And here's a kind of fun thing. This is big O of h cubed. Do you see that? Because when I integrate the h squared, I basically incur another factor of h. We're getting there, I promise. Okay. Page 3. So, right. So basically, the term that we need to figure out how to approximate is this integral here. We're almost done. And so let's do that next. Oh, this is a luxury. When I last taught this, I only had one backboard. That was really horrifying. So we now have the integral from tk to tk plus 1 of a prime of tau times tau minus h gamma minus tk d tau, like that. Now here's kind of a fun thing that I can do. I'm going to start using logic that we've already applied in today's lecture. Namely, here's the thing that we can write is that this is the same as the integral from tk to tk plus 1 of a prime of tk plus h gamma plus big O of h. Right? This is the same logic that we've used a bunch of times, like for Hoynes' method, multiplied by, well, the same thing we had before, tau minus h gamma minus tk d tau. Now, tau minus tk, if you think about it, this is big O of h. Do you see that? Because tau minus tk is the difference between some number between tk and tk plus 1, right? So that's upper bounded by h, and this thing has an h next to it. So that's in good shape. So let's try to see if we can leverage that a little bit. So in particular, if I write this expression here, notice I've got an order h here and order h squared there. So I have an order h squared on the outside. But in fact, it's an order h cubed because it's also integrated over time. So what I'm going to have is this guy is now a constant. There's no tau dependence. So I have a prime of tk plus h gamma times the integral from tk to tk plus 1 of just this expression, tau minus h gamma minus tk. I promise we're almost done with this ugly math. D tau plus order h cubed. So what did I do? I pulled this constant out, right? That left this term in the integrand. And then I have big O of h times big O of h times big O of h, which gave us the cubic term there. Almost there. Now here's the good news. Finally, this is an integral we can do. Do you see that? This is just a function, right? So in particular, what we get is going to be 1/2 a prime of tk plus h gamma times h squared, 1 minus 2 gamma plus order h cubed. And all this is I just did this integral in closed form. That's it. Here's a fun thing. This is equal to big O of h to the p. Right? Notice that I've got an h here. So here's how we do it. We say p is equal to 3 if gamma is equal to 1/2, p is equal to 2 otherwise. Does that make sense? Basically, when gamma is equal to 1/2, this term just vanishes, and I'm left with a cubic. When gamma is anything other than 1/2, I just get something quadratic. Turns out, sadly, we had to do all of that work for this expression. Okay. Now, we're low on time, so we're going to skip an argument which basically repeats the entire last two boards, but does it for a slightly different linear combination. In particular, Where was I? If we go all the way back to our expression up here, what we might want to approximate is this quantity here. Notice that we did all of this work here to approximate the difference between VKs. We could do similar amount of work to approximate the difference between YKs. In order to do that, we do almost an identical argument, but now our integrator for A contains this funny factor sitting in front of it. That's the only difference. Okay? So this argument is clearly in the textbook, but because we're low on time, we are going to skip because it's literally the same thing. And basically, what we're going to find is as follows. We're going to choose beta, which is kind of like the gamma that we had before. So like in our argument, it would be the analog of gamma for this thing here. Then essentially what we're going to find is the following little identity. The integral from tk to tk plus 1 of tk plus 1 minus ta of t, which hopefully is what we actually wanted. Yes. This thing is going to equal 1/2, I promise we're almost done, 1 minus beta h squared ak plus 1/2 beta h squared ak plus 1 plus order h cubed. And really all that matters is that cube. Okay? So I promise, like, there's no reason you should be able to derive this in your head. This is the one formula I'm just going to give you. It's in the book, and it's really just an analog of the previous two boards. Okay? So with all of these things together, I can take this integral, substitute it here, and our derivation of the Newmark integrator is done, which is good because we have 3 minutes left, which is exactly what I planned, of course. So in particular, what do we know? We know yk plus 1 is equal to yk plus hvk plus the integral from tk to tk plus 1 of tk plus 1 minus t times a of t dt. That is just copying this formula from the board up there. Yeah? And now I can drop this guy in here. And then, ta-da, we have our Newmark integrator. So in particular, this is yk plus hvk plus 1/2 h squared 1 minus 2 beta. I promise there's a reason we're doing this. ak plus 2 beta ak plus 1 plus order h cubed. Don't worry, it's all in the book, I promise. Okay, here's the good news. We're done. So in particular, the good news is also on my slides because I know my handwriting here is really horrifying. Here's what we do is basically just a whole set of ugly integrals. And what we get is a bunch of expressions here. And notice that for every beta and gamma, I get a different set of relationships between y, v, and a. Moreover, why do we do all of this work? I mean, this feels ugly, and that's because it is. I mean, essentially what Newmark did is he took like the last 10 integrators and then showed you can derive them all in one shot if you're willing to do one horrifying argument instead of 10 okay arguments. But essentially, here's what you can see. Notice that for any choice of beta and gamma here, by the way, we eliminated tau, which is good because it was like a weird constant. For any choice of beta and gamma, this basically gives you a completely determined system for obtaining the state of your system, namely y, v, and a, at time k plus 1, given the state at time k. This is a square system of equations. That's everything you need. And here's the kind of fun thing. For different beta and gamma, you get integrator with different properties. So for example, we already kind of showed along the way that we get a high order integrator so long as gamma is equal to 1/2. That probably went by a little quickly, but notice that that was there in our proof. If you watch my video from last year, it wasn't. I got to the end of this proof, and then I was like, oh, wait a second. That defeats the purpose of deriving this integrator. But moreover, we can actually derive a whole lot of fun things. So for example, If beta and gamma are equal to 0, we get something called a constant acceleration integrator. Notice this is a great example of philosophy that we talked about before, where we have a second-order Taylor series for y and a first-order Taylor series for v. So we expect y to be more accurate than v, which is kind of cool. If we take beta to equal 1/2 and gamma to be 1, you get something called constant implicit acceleration integrator. These are basically like fun mashups of the integrators we talked about before. So this is backward Euler for velocity and midpoint for position, which is what gives you that higher order accuracy. You can get the trapezoid integrator that we already derived as a special case of this thing. Here's one that looks like central differencing. Here I've reindexed to the k's to have a 2 in them, but that's not a big deal. But essentially the kind of takeaway is that for all of this math, you actually get a giant class of different numerical integrators with different properties. They are second order accurate exactly when gamma is 1/2. That's what we showed here. By the way, when I say second order accurate, I mean for y. V is still just first order accurate. That's kind of cool here. Moreover, you can actually show, we will not show it in today's lecture because enough already, that they're unconditionally stable so long as 4 beta is greater than 2 gamma is greater than 1. If you were able to guess that, then you're some freak of nature. Like that shouldn't be particularly obvious here. Okay, so with that, we have finished our penultimate lecture for this course. And the kind of fun thing here is now you have basically all the language you need to derive almost any second order integrator for ODE. This Newmark class covers almost every single one that you might care about. Moreover, there's really beautiful properties. In addition to the ones we've shown here, these are also variational integrators, so they actually preserve momentum for any choice of beta and gamma, which is kind of surprising if you care about physics. In our next lecture, we are going to cover one more integrator. I can't help it, I'm an addict, I'm sorry. But in particular, we're going to talk about the leapfrog integrator for ODE, which is the most famous one for solving Newton's laws, so it's worth mentioning. And then I think we'll put a fork in it. But in particular, in our final lecture, as one last topic, the sort of crowning achievement of this course, to put everything we talked about together, which we can try to do next time just for fun, is we can talk about sensitivity analysis for ordinary differential equation, which is a fancy way of saying, let's say that I want to solve an optimization problem whose variables satisfy an ODE. So think about, for example, I'm throwing a basketball and I have the angle of my arm, or whatever it is that people do with basketballs, and they throw this thing, and the optimization variable is like how hard I push, and my objective function has to do with the configuration of my basketball at time 1, right? So I have to solve a numerical integrator and then evaluate my loss function. The question is, how do I differentiate through that? If you think about that, that is going to glue together every single thing that we've done in this course. And moreover, it is the formula behind a very popular series of papers in machine learning domain called neural ODE, which do exactly that. So that's going to be our goal for our next time, is to talk about that thing. We're going to need a little bit of variational calculus for that, so get excited. And then with that, we will be done. And your TAs will have review sessions, and you can never think about numerics again. So with that, have a delightful rest of your Monday, and I will see you on Wednesday.